product of two things that are parallel is 0. So there's no force on a field-aligned current. So the superimposition of the circular component with the linear component for an arbitrary angle of input of current is, of course, circle plus straight line as a helix. Now, why they form in pairs is not an easy question. They do. And that's a laboratory finding. The little curve on the right just shows that if these things get too far apart, there seems to be a force that pulls them back together. If they get too close together, there's a force that pushes them apart. So you see them very often in parallel pairs like this. Here is an example, I think, of a classic example of Birkeland current. If you can see, I don't know how good your eyes are, or how good the slide is, but can you see the two parallel? Do you see the twists? This came from Göran Schammer's Solar Physics Institute in Sweden. And when they saw this, they described it as two parallel snakes with a stripe down their back, and they're twisting. I submit in this day and age they should know how to recognize a Birkeland current. But the properties are all there. So this is, I won't talk too much technically about it, but for those electrical engineers in the group, you recognize the voltampere characteristic of a Crookes tube discharge. This is essentially describes plasma. You can see that it's clearly a highly nonlinear, it's a laughably nonlinear kind of stuff. A resistor would plot out on this plot as a straight line. So clearly there are three operating modes for plasma, the so-called dark mode on the left, the glow mode in the middle, and the arc mode over here. And there seems to be abrupt transitions between those modes. If you have a plasma and make it operate in the range B to C, that's where Geiger counters operate. That's the so-called current saturation region. Because clearly, excuse me, you can change the voltage or the E field inside the plasma quite a bit and not get much change in current. But if you get an alpha particle that comes screaming through the plasma, it'll ionize one of the atoms and click, you'll get a click or a buzz or whatever. Up at the top is the so-called Townsend discharge. This is the region where it used to be called, what is it, St. Elmo's fire on the top of a wooden mast of a ship. The example of plasma in the dark mode is our ionosphere, as long as there's no aurora in there. But obviously, how do you know it's there? Well, you can bounce radio waves off it. If you're a ham radio operator like I am, you can, if things are right and the sun is doing the right thing, which it isn't now, you can get F2 refraction from the ionosphere and talk to Australia. So you know that there's dark mode plasma there, but that's the only way we can tell. The glow mode, that's easy. That's an example of that would be the neon sign. You know, eat at Joe's. That's a glow mode plasma. So I maintain is the corona of the sun. Arc mode plasma, that's also easy. That's the electric arc welding machine. It's also lightning. It's also the spark that you see when you scuff your feet across the rug in a winter night and reach out and touch the doorknob. That's plasma in the arc mode. A couple of things that are not too obvious, though, but I would like to point them out, and that is that at no point, except for the origin, which is not really very interesting because it says there's no voltage and no current, so there's nothing going on in the plasma. You're lucky to have a plasma at all. But at all the other points in that characteristic, there is no point that does not have a finite, non-zero electric field. And so don't let me hear anybody ever say that the electric field must be zero in a plasma. There's laboratory evidence that says that isn't true. As a result, for those of you who, we'll talk a little bit about this in a minute, but for those of you who know Maxwell's equations, the curl of E equals is proportional to the time derivative of the flux density. That's the excuse why people say magnetic fields are frozen into plasmas. Because if the electric field is zero, then the curl of zero is zero. And so if 0 equals the time derivative of something, it means that something ain't moving. So the magnetic field has to be frozen. Well, that puts the error to that argument. There is no place where the electric field is 0. Another thing you might notice is that, for example, in a couple of ranges, f to g and I to j, the slope of the curve is negative. The slope of that curve is the dynamic resistance of that stuff. And what you're really saying is, if you're in a point in the plasma operating at, say, point F, and you've got this bunch of ions and electrons dancing around each other, the E field on those particles is the force per unit charge on each of those particles. And clearly, a population of things will move to reduce the force on them. In other words, if you push on me, I'm going to move back. And electrons are the same way, and so are positive ions. So the plasma has a tendency to move from point F to point G. It wants to reduce the force on each of me. Well, how does it do that? Well, it's got to raise the current density. What's current density? Current density is how many amperes per square unit of area do you have? So what does the plasma do? It decides voluntarily, if you will, not to use the entire cross-section of the plasma, but to use a lower cross-section. So it increases the current density by reducing the area that it uses. In other words, it forms filaments. So a natural tendency of plasma is to become filamentary, at least in the low current density range of the normal glow mode and in all of the arc mode. So people talk about sheet lightning, but I have a sinking suspicion that that's a certain form of glow discharge, not arc discharge. Most lightning strokes are filaments, jagged three-dimensional filament, very narrow. Okay, enough of the physics. Oh, just some plasma properties. I hope to go through this relatively quickly because I've got more interesting things and I don't want to overstate my time. I think we've talked about most of those things, if not. Oh, by the way, electrostatic analyses usually fail. Most people look at some of the things that plasma physicists do and they say, oh, that can't happen because if you use the equation Q1, Q2 over R squared, they'll go together, they'll separate. Plasma forms cells and insulates regions of plasma from nearby regions of plasma, just like blood does. So simple electrostatic analyses usually fail when they try to use it. You've all probably heard this one. Here's a pair of copper balls, like little billiard balls, more like shotgun pellets of copper. If you remove one valence electron from both of those spheres, you will levitate the top against the entire pull of the planet Earth to pull it down. One electron out of the some almost 6 trillion that are in there available will levitate that copper ball. On the other hand, if you take the electron from the top one and place it on the bottom one, then you'll have on-like charges and they'll slap together with twice the weight of the original one. So this is a slide that people in my side of the fence use to show that electric force is much, much more powerful than gravity. But then the argument is turned right around and used against this by people who say, well, yeah, so therefore, if it's that strong, you can't have charge separation in space. Pluses and minuses will come together. Well, that isn't necessarily true because we do have plasma in space. But this was the primary criticism, as I referred to before, against Birkeland's idea that stuff was coming from the sun. There is a sort of a dichotomy between the theoreticians who claim to be plasma scientists but who never want to get near a laboratory and the experimentalists, the experimental guys who are in the laboratory. Most of the assumptions that are made, because you want to use magnetohydrodynamics, is you use a homogeneous model. Well, it turns out that plasma is almost never homogeneous. The conductivity is infinite. No, it's not. It's not infinite. You saw that volt-ampere characteristic. There's a finite non-zero resistance to every point in the plasma. The E field along B is 0.